that you should care about the thermosphere and things happening in the thermosphere from a space weather perspective a bit more. I mean, maybe you already care, but I'd like to like convince everyone who maybe doesn't care as much to care. Because in our field, I guess, when we think about space weather, we often think about like magnetosphere-ionosphere coupling and all the complicated like cross-scale things that are going on in those systems. But the thermosphere kind of often feels a bit like the forgotten brother in that sense of it. So I'd like to kind of convince you today that thermospheric dynamics, particularly at the high latitudes, is not only important, but also very, very impactful on a lot of things that we take for granted when we think about the magnetosphere and the ionosphere. So I'm going to try and like connect it to the two. So the obvious like cheat answer of why the thermosphere is important is because of the thing that happened 2 years ago in February 2022 when SpaceX launched a bunch of Starlink satellites straight into a couple of geomagnetic storms. This was, at the end of the day, this was because of what was going on in the thermosphere. And I'll talk more about like the data behind it later on. But in short, the geomagnetic storms happened, thermospheric mass density raised to a point where there was too much drag on the spacecraft, so that they then re-entered several days later. Because this is SpaceX, it got quite a lot of media attention, and for quite a good reason. So this is a slide I've shown quite a few times before, doing some back of the envelope maths on how much that like event where the Starlink satellites got destroyed cost. And according to some educated guesses from a few sources, it looks like it's about 19 million US dollars when you take into account the cost of the satellites. Cost of launch is about 15 million US dollars in Canadian. That's about $47 million. Putting this in a bit more context, that's about 0.0007 of what Elon Musk paid for Twitter. Maybe in more depressing context, that's about 627 years worth of Canadian Space Agency, like general solar terrestrial research funding. It's a bit less for NASA because you Americans get more money. Or maybe even more depressing, because I showed this to a bunch of students at the university. It's about nearly 6,000 years of student tuition fees at the University of Saskatchewan. So that, in my opinion, no, that's a lot of money, obviously. It's a good reason to like look at thermospheric dynamics more seriously. And of course, this Starlink event happened. So it's also a good thing that we can like look back on and then, put in grants and stuff like that and say, here's like a recent example of why like space weather research, magnetosphere, ionosphere stuff is important. So the thermosphere is really, really complicated. And what's important with regards to space weather and magnetosphere-ionosphere coupling depends very, very heavily on latitude. I obviously can't like cover everything in this like talk, though I think I'm going a bit fast, so maybe I can like answer some questions later. But I'm just going to talk about like the things that I have experiencing, and that's talking about like the density, so the thermospheric mass density, just the density of the air as it goes up in altitude, it gets lower and lower, and then neutral winds, which are almost equally as important as like what the density is doing, in my opinion. So, why do we care about the neutrals? Well, the short answer to why we care about the neutrals is because they occupy the exact same space as the ionosphere. So in the ionosphere, you have all these, charged particles which do crazy things because they're, coupled very, very strongly to the magnetosphere and the solar wind. There's O plus, N2, nitric oxide, and they're all frozen in and do all the crazy ionosphere stuff, do aurora things. And then you have like the seemingly boring neutral particles, which aren't ionized, oxygen, nitrogen, helium, which is basically just like air, but at a lower density. And most people think about thermospheric neutrals and they think about just Earth processes. So they're called neutral winds. So you think winds and you think, okay, they're maybe affected by the Coriolis force or they're affected by like diurnal tides, and they are, but it gets a lot more complicated by that because of this presence of the ionosphere, which is so strongly like linked to what's happening out in space. Um, so when you have a partially ionized plasma and a perpendicular magnetic field, which is what the thermosphere is, it's a partially ionized plasma. You get collisions between the ions and neutrals, and then because of that, you get a current set up in the ionosphere. That current is dissipative. That's the Peterson current, not the Hall current. And the energy that gets released when ions and neutrals collide is Joule heating. And now Joule heating is considered by many like this really fundamental number just in like space weather, magnetosphere, ionosphere, thermosphere science, which we all understand, want to understand, because the amount of Joule heating is the amount of electromagnetic energy which is being deposited into the atmosphere because of space weather. So when we talk about like geomagnetic storms, increasing the density and, causing satellites to come down, that's because of Joule heating at the end of the day. It's this extra energy being deposited, which is affecting the atmosphere and affecting the regime that the satellites are in. So um, this is like a little schematic that I drew up again for like an older seminar where, you have ions floating around, you have neutrals floating around, they collide each other and then, they go off in their separate directions, and there's some amount of energy which is lost as heat in that process, which is the Joule heating. But it's intrinsically this process, and the amount of Joule heating you get is intrinsically dependent on the speed at which those ions and those neutrals are moving prior to when they collide. So the ion drift, that's something a bit more well understood than the neutral winds. This is just the maths behind the Joule heating because it's the power in watts dissipated per unit volume. That's this dP dV. And then when you expand that out, taking the power is the current times the voltage. This is voltage now, not volume. You get the current density, this J dot E term, where E is the electric field. And then when you expand that out again, you can turn, this electric field into two components. So I've turned it into two components here. One which I've called the convection electric field, and then this U cross B term, which is an electric field again, but it's the electric field driven by ion neutral collisions, because if the neutrals hit ions, then those ions are going to be moving through a magnetic field and generate an electric field. So this part on the right, this thing where I've got a type of wind dynamo electric field, that is basically the component of the Joule heating equation, which captures the ion neutral collisions. So first, the easy part, the convection electric field. That's probably the most understood part because it's just, this big Dungy cycle magnetospheric convection, which then maps down into the ionosphere and causes the ions to circulate. So in this schematic here, at A, you have day-side reconnection, which opens up flux in the day-side ionosphere. And then that kind of differential of pressure causes ions to start drifting anti-sunward. At E, which is on the night side of the magnetotail, you get the closing of flux, which starts taking away that energy from the ionospheric polar cap, so causing ions to kind of drift out. And then when you have a combination of the two, so like under perfectly southward IMF with day-side reconnection and night-side reconnection, you get this like ionospheric circulation pattern, which is the convection, the ionospheric convection. So statistically, so this one on the left, this is what happens when we just like take all the data that we can from ionospheric drifts and we like bin them by solar wind clock angle. And that's when you get this, ionospheric convection circulation, which is so strongly dependent on the orientation of the IMF, because that reconnection point changes depending on BY and BZ and, all those things. So you can do that statistically, or you can look at that within data, which is what I've always done a lot in. I work with Superdarn Canada, so you can make up these global instantaneous convection patterns of the ionospheric drift just by collecting data from all the ground-based radars. So you can get an idea of what the ions do statistically, just by putting all the data together, and you can get it for a single moment. So this is kind of the straightforward part of the Joule heating equation, because the ion drift is directly related to the electric field, because E equals minus V cross B. So we can just pull out the convection electric field straight away from that, and that's what's most commonly used. So that's that part of the Joule heating equation. But what about the neutral wind part, that dynamo electric field? So you may be thinking, the neutral winds are slow compared to the ion drifts, so I'll just set them to 0. And I wouldn't blame you if you did that, because I've actually read like many, many papers published over the last couple of decades saying that exact same thing. They take this U cross B component of the Joule heating equation, and they just say neutral winds are slow. I'll just set it to 0. There's several reasons why people drop the winds, because generally at lower latitudes they are quite slow. At higher latitudes they're not, so that that assumption doesn't really hold. But the second reason why people drop the neutral wind part is because actually it's very, very difficult to get neutral wind measurements. So instead of trying to account for that, it's just often easier to throw it away and forget about it. So I'm going to talk a little bit about what the winds look like, and kind of how we get data for that now. So this at the top here. I can't get my mouse to come over for some reason. But this is just the neutral momentum equation, just when you work out the acceleration on a single neutral particle, and you look at all the components about what would affect that. So we have this rho g, where g is the gravitational constant, so that's just the gravity does. That's very easy to understand because g is a constant, and density might fluctuate, but in general it's very slow to fluctuate, so we can do that pretty well. We have this del P component, which is pressure gradients. So that's if you have a hot region of air and a colder region of air, and then the neutrals will just want to fly away from the hot region to the cold region. So you get that in the thermosphere because you have one side of the Earth which is lit by the sun, and the other half that doesn't. So you get this general anti-sunward motion of winds. That's also very easy to understand. We have the Coriolis component, which is dependent on the angular rotation of the Earth. That's also very easy to understand. We've understood Coriolis forces for a very long time. And then this final component, which is generally pretty small, you can get forces on the acceleration of the wind due to shears. So winds going in different directions, kind of affecting each other a little bit. Now, you can see the effects of all these components. I haven't talked about this last one, ion drag, because I'll get that to it in a second. You can see the effect of all these components on the neutral winds. This one on the left, the schematic on the left, kind of shows the general direction that all those things move in. Like I said, pressure gradients are usually anti-sunward. So you take the hottest region of the thermosphere and you say the winds are moving away from that region. You have Coriolis forces, which is pretty much fixed direction depending on the location of the Earth you're in. And, depending on the direction of the wind itself, it circulates in the Coriolis direction. And then this other one I have in here, ion drag, which is probably the single reason why the neutral winds are so difficult to understand, because ion drag is the force the neutrals experience because of those collisions with the ions I talked about earlier. So if you go back to this flow of the ion drift, which we can measure with Supernon or whatever satellites that are measuring the ion drift, and then you go back here and you look at it, okay, every time these ions are going to collide with the neutrals, some of that momentum is going to be imparted to the neutrals. So some of the there is going to be some force pushing on the neutrals in the direction that the ions are moving. So in this circulation pattern that something like Supernon measures. So when you look at statistics of neutral winds, because that's kind of the best thing you can do if you want to look at data for the neutral winds globally, this is a statistical pattern from, I think it was the CHAMP satellite. from like a decade or so ago. You can see the effect of ion drag here because it's these two circles on the dawn and dusk side, which I've pointed to as arrows here, kind of making the neutral winds kind of turn into this vortex. That's ion drag because that's also the direction of, plasma flows. So that's all well and good um, to look at statistically, because we have these plasma and neutrals colliding. The rate at which they collide is dependent on the ion neutral collision frequency. Just this term I've pulled out on the bottom here, the velocity of the ions, the velocity of the neutrals, and the collision frequency between the two. That's the most basic way you treat ion drag. But statistically, statistically never happens, right? Because we know the drift of the ions, you know, could be considered better behaved than the neutral winds. But statistically, we don't actually see much difference between you know, how the neutral winds look at different IMF clock angles, which we know the ions are very heavily controlled by. We don't really see that kind of difference very, very strongly in the neutral winds. You see it like very, very slightly, but it's not actually that significant. And the reason behind that is because the ions just are so variable, right? You go from one IMF clock angle, say from northward IMF to southward IMF, or vice versa. Going from southward to northward IMF is like switching off dayside reconnection, and then sometime later switching off nightside reconnection. That completely changes the pattern of ionospheric convection from this one on the bottom, this southward IMF, to this one on the top, which is completely different. But because the neutrals are so heavy and have so much inertia, um, they just can't respond as quickly. So you have this dynamic where the ionosphere is changing so quickly, but the thermosphere can't react. And so that comes back to when we come back to Joule heating, and then we look at this Joule heating equation again. I've just expanded it out into its height integrated form. So this component on the left, which I've marked QC, that I've called convection heating, that's just the Joule heating if you just take the ion drift, which, like I said, a lot of papers over the last several decades do. They just take this one component here. When you factor in this part on the right, which is the stuff with the neutral winds, it gets extremely complicated on what the Joule heating looks like. Because here's two scenarios I've got down here in this little schematic. If you have on the one on the left, the neutrals and the ionospheric convection going exactly the same direction and at exactly the same speed, so the blue arrows and the black arrows going, exactly the same speed, then your Joule heating is zero in that sense because you have no collisions. Or you do have collisions, but because they're going the same speed, there's no momentum transfer. So the net Joule heating over this whole hemisphere is zero. This one on the right, if they're going different speeds, which they always are, you get Joule heating because essentially the amount of Joule heating you get is the differential between the ion drift and the neutral winds. And the bigger that differential, the more Joule heating you get, or the lower that differential, you might get no Joule heating. So you can see that if you just ignore this QC part, the convection heating, without taking into account the neutral winds, you can both severely underestimate and overestimate the Joule heating under different scenarios. So I have now this case study from something we did a few years ago. This is using Superdawn. So each of these panels here are like successive like 10-minute integrations, I suppose. This is using Superdawn radars at Thikvi and Hankasami for the ion drifts. And then for the neutral winds, we use what's called a scanning Doppler imager. It's a type of Fabry-Perot interferometer, but it basically gives us neutral wind vectors in all of these like sectors that are drawn over Svalbard. And then on the right, in each of these panels, that's what each of those green vectors are. Those are the neutral winds measured by the scanning Doppler imager. The white contours in the background is Superdawn. So that's the ion drifts. Superdawn saying which way the ions are moving. And then the coloring is then an auroral imager, which is on Svalbard. So I will just go to the the really good bit here. Um, in this one on the left, the 716, you have neutral winds going almost towards the dusk side a little bit, where the ion drift, so the contours going by supernaut, are kind of going dawnward a little bit. Um, Sometime later, there was some aurora, and we know that aurora increases the plasma density, which will in turn increase the collision frequency. And so if the collision frequency goes up, that means the strength of ion neutral coupling and ion drag goes up. So between these two integrations, you see the neutral wind change from completely going duskward a little bit to going and curving in the direction of the superdarn convection contours. So that is the aurora increasing the conductivity, increasing ion drag, and then pulling the neutral winds along with them in a very, very short period of time. What does that mean for Joule heating? Well, it actually means the Joule heating goes down, which is actually very contrary to what we might think happens when you have aurora. Because usually you think, okay, aurora, conductivity goes up, plasma density goes up, I should have more Joule heating. Well, here it's the opposite. So at this 716 panel, the one on the top is just the one I showed earlier, and then the one on the bottom is what I get when I calculate Joule heating using the conductivity estimates from the aurora, using the neutral winds, and using the ionospheric drifts from superdawn. So at 716, we get some Joule heating because the ions are moving one direction and the neutrals are moving another. And then at 745, we basically have no Joule heating because the aurora has caused the coupling to increase so much that the neutrals get pulled into the ion drift direction. And that decreases the Joule heating like completely. So this was like a really, really nice find we have because it's like it's the ionosphere and thermosphere being very, very reactive to each other. We've got measurements of basically every component of this system, in a very, very small region of space. But we can see here that the amount of energy that's actually getting like deposited into the atmosphere is decreasing in this scenario, and we wouldn't have seen that if we didn't take into account the neutral winds. So, as you can imagine from like this example and kind of like what I've talked about, is it's not a straightforward exercise to get accurate Joule heating measurements if you don't have neutral winds, because the relationship with ion drag is complicated. It's dependent on the conductivity, which is also hard to know. It's dependent on the collision frequency, which is usually a best guess. And some people might like take MSIS or something like that to get an estimate. But hopefully, like from this, you can see that if you're doing an event case study, that's not really sufficient. And you might be thinking, okay, that's just an event. What about statistically? Surely the neutral winds don't have really much of an effect statistically. Well, they do, because here on the left is what I get when I calculate the Joule heating statistically using superdarn and using that conductivity and electric field without neutral winds. And then on the right, that's the statistical Joule heating. This is from like 2 decades of superdarn data. But on the right, this is what happens when I take into account neutral winds with a empirical neutral wind model. And obviously, this is a huge difference, right? We basically remove all this Joule heating that is happening on the dusk side when we include neutral winds, and then we enhance the neutral winds on the dawn side. And that's actually its own kind of interesting thing that generally happens statistically, because on the dawn side, ion drag is usually acting in against the Coriolis force, whereas on the dusk side, ion drag is acting in the same direction as the Coriolis force. So those kind of superimpose on each other on the dusk side and end up decreasing the Joule heating, whereas on the dawn side, they're acting against each other. So you get this bigger differential between the ions and neutrals, and you get more Joule heating. So it's really, really complicated, is what I want to get across, because you have all these competing forces, not just ion drag. You have the magnetosphere imposing stuff on the plasma, which is then doing ion drag. But then you have, solar pressure, which varies with season and UT, and then you have the Coriolis force, which varies with latitude. It's very, very confusing and hard to like get a good grip on this. But anyway, the whole point of this, I'm getting back to like the density side of things, is Joule heating is important to get right, because it is ultimately what is responsible for that Starlink event, which happened a couple of years ago. This on the left is statistics for the Poynting flux, which is not joule heating. A lot of people treat Poynting flux the same as joule heating, but they're not exactly the same thing. It's the difference between the work that's getting done and the work that's actually being dissipated. But usually most of the Poynting flux is joule heating, which is why I've shown it here, and just because it's easier for me right now. But if you look at some statistics for like where the variability of the joule heating has happened, so where the electric field is most variable, and then you compare that to where the neutral density is most enhanced. So that's this plot on the right, and this is from some CHAMP statistics we did a few years ago. You see that the joule heating, or the variability of the joule heating, corresponds very, very well to the increase of thermospheric density. And this is the fairly well-known cusp neutral density enhancement. This is like attributed to basically variability in the electric field, which increases the joule heating and then increases the density because joule heating comes down, it deposits somewhere in the E region because that's where the Peterson conductance is highest, because that's where the density of the neutrals and the ions like become comparable. So they start like creating a very, very parallel Peterson current. And you get this upwelling. So the heating just literally causes the air in the thermosphere to rise. Density decreases exponentially with latitude. So you get this dense air lower rising up. So actually untangling why the density increased is very, very difficult because the density is dependent on, well, the usual diurnal density is dependent on like season and solar irradiance, but then how the density varies due to geomagnetic activity is dependent on the joule heating, which is then dependent on the neutral winds, which is dependent on ion drag, Coriolis force, pressure gradients. So it's really, really complicated. So let's go back to this. The February 2022 geomagnetic storm, which caused the Starlink satellites to, come down because there was an increased density. Here's like a nice video taken from Puerto Rico of that, and I like to show this every time I talk about this event because this is just such like a stunning example of like our research having like real, impacts that we can like point to, and I also like it just because I like fireworks, and this is like kind of close to that. So Starlink couldn't maintain their altitude in February 2022 because there was an increase of the density at their staging altitude of about 210 kilometers. So here I'm showing two like global density like data. So this is like latitude on the y-axis versus time on the x-axis. These are density measurements from the accelerometers on board Grace FO, which are around 500 kilometers altitude, and then Swarm C, the ESA mission, around 450 kilometers. So, and then on the top here, I've got just the SIMH index. So that's just showing our geomagnetic storms happening on the 3rd, and then one again on the 4th of February. So staging the satellites around 210 kilometers is quite cheap for Starlink because 210 is quite low as LEO satellites go. So they put them at 210 and then they do all their in-flight corrections and then they boost them up to a higher altitude of about 500 kilometers later. But 210 kilometers is obviously very low as far as thermosphere goes. Can't really stay there for long under normal conditions. So when you get a lot of joule heating, which is happening in the E region around 110 kilometers, that's going to put a lot of risk to these satellites that are at 210 kilometers. And a little footnote for this is that after this whole event happened, SpaceX did in fact start launching their satellites at a higher staging altitude. So here are the neutral densities on launch day. So the top panel is, or the first and the third panel are the absolute densities from Grace and Swarm. And then also I've put the blue line is the quiet time values from MSIS. And then the second and fourth panel are perturbation densities. So that's what we get when we subtract the quiet time densities from MSIS, and then we do it as a percentage. So how much of a percent has the density increased? And you can see from this that yes, the thermospheric density was indeed significantly higher than it would be under quiet conditions. We see from GRACE and SWARM that the orbit average went up to about 100% increase. But then if you take into account like single point measurements, so like when it comes up to the northern or southern hemisphere high latitudes, it actually goes up to several 100% of a density perturbation. So let's look at, so all of those densities went up because of high latitude driving, right? The magnetosphere is coupled to the high latitude ionosphere, which is doing that convection pattern. Unfortunately, so I work with Supernon, and I did initially look at Supernon data for this event, and I would have used it if I could, because obviously I'm contractually obliged to use Supernon data, but the Supernon data was kind of bad for that event. So instead, I went with Ampere. Some people probably know what Ampere is. It's this global experiment that's using the magnetometer data from Iridium's constellation of communication satellites. And then it takes all those magnetic field measurements, subtracts a background magnetic field, and then gets the perturbation due to the field line currents. And the field line currents are, for my purposes, basically the same as the ionospheric convection, because the field line currents come in and then they're, coupled to the same region, the same regions of the convection. So for all intents and purposes, these field line current patterns from Ampere are my measure of the amount of the activity that's going on in the high latitude ionosphere and the amount of Joule heating that's going into it. And I understand, and someone's probably going to point this out to me, that in doing this, I'm actually not taking into account neutral winds, which I've just been going on about for like the last 30 minutes, talking about how important they are. I fully get the hypocrisy of that, but I'm using it just as like a ballpark, field line currents go up, Joule heating goes up in this scenario. So here I show the launch day neutral densities again, this time only from Swarm C, the perturbation densities, but now also coincided with these dusk dawn kilograms of the Ampere field line currents. So I've just taken a slice of the field line currents going from the dusk side over to the dawn side. And unsurprisingly, because it's a geomagnetic storm, we see the field line currents from both hemispheres. So I've got the northern and southern hemispheres here. We see the field line currents, they're strong. And because they're strong, we have higher Poynting flux and then higher Joule heating. And so I guess what I want to stress out with this one is the field line currents, they become enhanced very early on in the day in both hemispheres. So, we see them strong field line currents from about 4 UT onwards. But then the thermospheric density takes several hours to reach a peak. It peaks where I've put this blue shaded region here around 12 UT. That's again like owing to that adds into the complexity of understanding things going on in thermosphere, because everything is taking several hours to reach like a maximum. If you have the exact same input happening in the ionosphere for several hours, it's not going to show in the thermosphere for several hours. So that again makes things more complicated. And we also see like this asymmetry in the field line currents, which I'm going to get into about later, because that does actually come across in the densities. And then the field line currents dissipate very quickly after about this blue time. But then again, the density takes a very long time to kind of settle down. This is the day after launch when that second geomagnetic storm happens, and we got a very similar story. So the field line currents intensify, they stay enhanced pretty much this whole day. They peak around, 19, the density peaks around 19 UT. But what I want to show with this one is if we go to the day after this, so 2 days after launch, it becomes really clear that the density stays high, even though there's seemingly no geomagnetic driving happening. Because the day after, we pretty much, if you just looked at the field line currents for this day and you didn't look at the density, you'd say, okay, this is a quiet day, not a lot going on. But then if you just looked at the density, you would see this starting with 100% enhancement and then coming down. And still by the end of the day, it's several tenths of percent enhanced above quiet time levels. So you would look at that and think, wow, there's a lot of activity going on there. But then if you didn't look at, what's going on in the ionosphere the day before, a whole 24 hours before, you would have no idea what was going on. So this is kind of goes to show, I guess, you can potentially conceive of a situation where you have enough geomagnetic activity, enough driving in the ionosphere to cause potentially unsafe thermospheric conditions for at least a day afterwards. I'm not saying this event did that because, in the grand scheme of things, these two geomagnetic storms are actually very, very minor. They don't even reach minus 100 sim H. But if you could conceive of a very, very powerful storm, then obviously these effects would be amplified, and you could potentially imagine unsafe thermospheric conditions for satellites for some amount of time. Um, and then this is just like my final set of like data plots, I guess, in this whole talk. Just talking about the hemispheric asymmetries that we saw when we were doing this, because I wanted to see um, what was the latitudinal distribution of the thermospheric density. And my original idea when I started this project was we know there are certain regions of the ionosphere where joule heating is higher. It's higher in the electrojets and it's higher in the cusp. So could we see density higher in those regions too? And unfortunately, because I'm using satellite data, the satellite's got its own orbit and it's seeing different local times every time it goes around, and it's a completely different day, different things are happening, so we can't really make any good kind of connections to where joule heating was high and where the density was high. But we could do this. What I've done here is I've just averaged by latitude for both Grace and Swarm for each day. So we've got the third launch day was on the 3rd, so I've shown 2 days before that, and then the subsequent days afterwards. And then surprise, surprise, we see that the thermospheric density is much more significantly enhanced at high latitudes, which is, where all the ionospheric activity is happening. And this also shows like quite a significant density asymmetry as well, where the perturbation density is actually higher in the northern hemisphere than it is in the southern hemisphere. And because this is in February, so it's technically summer for the southern hemisphere, and winter for the northern hemisphere. So that probably has something to do with it, because the density is already a bit higher in the south because it's in sunlight. So potentially the perturbation that has to happen to the density to make it higher, that perturbation needs to be higher in the south than it would be in the north to generate as big an effect. And then you also see, like, if you look at the southern hemisphere, so the minus, these shaded blue region in the southern hemisphere for these plots, both satellites show this kind of interesting bump in the density that we saw, which, coincides pretty nicely with the cusp, which you don't really see in the northern hemisphere. It's more spread out. So that, and then, some of this could be related to the field line current asymmetries that we saw during these events as well, which we know is already a thing. And there's quite a few studies going around right now with asymmetries in the field line currents and atmospheric driving, which could have something to do with the asymmetries in the magnetic field in both hemispheres, which is like a whole nother layer of complexity, which you can add into all of this on top of it. And then I'll finish kind of, by showing this. This is a press release that SpaceX uploaded to their website like a few days after, the satellites re-entered. And then I'll just highlight this one little region here where they say SpaceX deploys its satellites into these lower orbits so that in very rare case that any satellite does not pass initial system checkouts, it will be quickly deorbited by atmospheric drag. So SpaceX, I guess, used this opportunity. They used this for a publicity opportunity and said, "Oh, look how economic and thinking of the world we are by saying, okay, we put it in a low orbit, because then if something does go wrong, it'll re-enter." And that is true. The satellites are cleaning up after themselves, but I'm not really sure if that's the intent, because they didn't really, because some things have come out after the fact since I actually made this, you know, these presentation slides like a while ago. Turns out that SpaceX, um, when they had them at 210 kilometers, and then they realized there was a geomagnetic storm and that the density was going to go up, they put the spacecraft into these low drag orientations. Um, and then once they put them in that orientation, and then eventually they wanted to boost them up to operational altitude, they couldn't get them out of that orientation. So through the grapevine, it seems this was more like an operational failure versus the density being so much in the thermosphere that the satellites couldn't take it. But then they wouldn't have, had to do that if they didn't launch them so low, or if they maybe anticipated that the geomagnetic storm was going to happen. And in fact, several days before the launch, NOAA did issue geomagnetic storms warnings for the day of the launch because they saw solar flares leaving the surface of the sun. So this was actually predicted, which is unusual, because we all know predicting space weather is very, very difficult. So ultimately, potentially this could have been something to avoid, and I think it will be something that they're doing a lot now to kind of avoid going forward in the future, because obviously it's a very costly mistake. So I will leave it there and just kind of leave you with three things that I want everyone to consider when they're kind of like looking to think about the thermosphere, like in their space weather, magnetosphere, ionosphere science. Um, the thermosphere is very, very difficult both to interpret, as we've seen, there's so many different forces playing a role in what happens to the winds and the densities, but it's also very, very difficult to measure. There are just not a lot of good, well, there are a lot of good instruments, but the way we measure the neutrals is so different to how we measure the ionosphere, because stuff happens in the ionosphere which we can measure, based on phenomena. Like we can use incoherent scatter radar, coherent scatter radar, or we have, satellites flying. And because it's electrodynamic, there are certain phenomena we can take advantage of to, get out ion properties from that. But with the neutrals, it's completely different. And right now we're kind of stuck with ground-based images, which obviously susceptible to optical effects and can't operate in daylight or can't operate if there's clouds. And then satellite accelerometers, which are good and probably the best thing we have to do neutral winds and densities. But again, those are single point measurements. So you can't do these large scale, global investigations or larger area investigations of what the winds are doing. So that's why I guess so much effort is going into looking at models of the neutral winds like TIGCM and others. Yeah, and we've got the thermosphere is, I hope that didn't turn you off talking about the thermosphere, because the thermosphere is also so interesting because it's where all these space forces interact with the terrestrial forces like the Coriolis and the solar pressure gradients and stuff like that. So it's a really good bridge between, our field of space weather and then, some of the lower atmosphere weather kind of things. And in that, like I'll also say that, if you do this, you have to use multiple instruments. So in all of my studies I do, I use Super Ampere, FiberPro interferometers. You have to use multiple instruments so you can have a multi view of the system, because as we saw earlier, you don't take into account neutral winds, then you might severely underestimate your joule heating. Or if you don't look at the ionosphere a day before, when you look at the thermosphere, you might miss important dynamics which happened, which cause the thermosphere to be as it is. So yeah, that's my presentation, and be happy to answer any questions, or you can also email me. I haven't actually put my email in here, but if you Google my name, it'll come up.
Thank you, Dan, for a really cool talk. We do have a couple of questions and comments. Hugh mentions, which you touched on here, terrestrial forces, that there are other heating terms that can lead to non-local energy losses of accelerated particles. Did you want to comment on any of those, or the relative importance, and how do you think they compete with the joule heating and the ion forces?
Yeah, it's all important. I've only talked about dual heating because that's kind of my thing, I guess. But yeah, you're right. There's like particle heating and other things because obviously when you have the aurora, you just have direct heating from that. But then that will also impact the neutral winds because any form of heating coming into the thermosphere will drive a pressure gradient. So uh, it's almost like a chicken and egg situation. If you think about ion drag, where ions force neutrals, like if the circulation of the ions or whatever force neutrals. But then if you have increased dual heating, which happens if you have strong electric fields or neutral winds going in different directions, which happens, if ion drag is misaligned, then you get extra heating. And then that extra heating itself will drive more winds because that's adding to the pressure gradient term. And then when you add when you have this pressure gradient term increasing the neutral winds, well, suddenly now you have more ion drag because the neutrals are going away from the ions, pulling them a little bit. Because remember, neutrals pull on the ions as well as the ions pulling on the neutrals. So it's you can't really figure out what's driving what because they're both driving each other. And
Mhm.
yeah, this extra heating that comes in is like a part of that and just makes it way more complicated. It's why you need so many lenses when you look at it through so many different instruments to get as complete a picture. You can't just say, oh, there's dual heating, so it did that, because it's never that simple.
Yeah. Yeah. And Hugh has a comment following on from one of your last slides there about
Oh, sorry, you've frozen. I don't know if it's
decay
frozen.
as well, or the loss, the environmental effect of deorbiting at the 200 kilometers that isn't always concerned.
Sorry, you froze at the start of what you were saying then.
Yeah, sorry, I'm getting bad internet at the moment. Hugh mentioned that the deorbiting at 200, while it is helpful, that there is some recent stuff in the news and in that there is an environmental effect for the deorbiting even at that altitude.
Right, yeah, I'm not too familiar with that. Honestly, but I would like if you want to like comment on that. I don't really know much about the like I'm assuming you're meaning like releasing some heavy metals into the atmosphere or something like that. So if
I'm not sure. Hugh, did you want to comment?
Yeah, that's what I meant. And the question is, do you deorbit to the perigee or do you deorbit to the apogee of these spacecraft? And obviously, the launch costs for deorbiting up and not down are very different. So, but I was just commenting on the news because in the last week there's been discussion about layers of strange elements appearing in the ionosphere or in the stratosphere, and
Oh, interesting. Yeah, I haven't seen that though. That's uh that's another thing, I guess. So maybe SpaceX aren't quite the champions of the environment that they wanted to kind of come across as, but
as you say, it's complicated. I have another question, if that's okay.
yeah.
Yep.
So I'm I'm certainly not in this field. I don't understand what you're talking about particularly in
Oh,
detail, but I'm a solar physicist, and so I'm just following up on solar flare effects as a measure of how big a solar flare is. And solar flare effects are a very nice punctuation, of the environment that you're interested in. So I'm wondering if there's data in Ampere that tells us about the field line currents that come from solar flares, or now just rush off after your very nice talk to look that up. So
oh,
what is your understanding of that kind of impulse response that you might enjoy?
um, I'm not sure like the direct, if someone's looked at like a catalog of solar flares and then looked at the Ampere response, I would be surprised if no one's looked at that because people have looked at like that in Superdan data and other things more from like I guess a geomagnetic storm point of view, like the flare drives a storm and the storm does this. I haven't seen anything specifically about you know um, flares or the types of flares having particular impacts, though I'm sure they do. Um,
It
because
could be
sorry,
it could be a subtle effect, but
right,
it might be quite interesting diagnostically in any case,
right,
because
yeah,
you know a great deal about the energy, about the the deposition was as a function of height and from the solar radiation.
Yeah, I suppose it will be an imposition of the interaction of like the CMEs or the I always get it mixed up. Flare is the what it looks like, and CME is the actual materials, or it's the other way around. I always get
No,
mixed
I'm
up.
talking about the flare effect. SFE is electromagnetic radiation.
Oh,
It's
the
actually
radiation, right?
Raman
Uh,
alpha and
yeah,
reflection.
I'm not sure though. I'm sure. Like I'll also Google this afterwards and just Google like ampere and solar
Great.
flares.
Okay, checking it out. Thank you.
Yeah.
We had one final comment from Patricia, which I think you also mentioned as one of your last talking points, is that you can also get some really interesting velocity changes in the dawn-dusk region, which can lead to very distinct changes in the Joule heating, which I think you touched base on and mentioned as a key component at the end here. I have one last question. You do say multi-instrument studies are really important, but what are your thoughts on new possible constellations to study this, given that the dynamics are so important, both in latitude and longitude, but also in altitude?
Very, very important. It's it's more data is always good, and obviously I'm excited for when and if GDC goes up, and the other missions that are like easy and some other things, but multiple. A big part of why this is so complicated and hard to understand is because we don't have the global measurements like we do with supernon and ampere. You can get a global instantaneous pattern of the ionosphere. Maybe it's large scale and maybe it's smoother and maybe it hides some small scale dynamics. But you just don't have anything like that for data for the neutral wind. I'm not sure if there'll ever be a point where we'll get that, but when you have something like, GDC, which is flying several satellites, side by side, trying to figure out the multi-scale properties of both the ions and the neutrals, then you can start to do some like really special things. And especially if there's still not going to be, it's not going to be completely solved. Obviously, you can't completely solve it because the satellites are going to fly around and then they're going to come around and then they're going to see the same region or a different region at a completely different time. So it's really going to help with the multi-scale aspect of things because the plasma we know is very, very structured across scales. The neutrals less so, but then we also know the neutrals can be slow or they can be fast to respond depending on situations. So it'll be. I'm really excited. Obviously, I think a lot of people are excited and want GDC and the other missions to succeed. So I'm looking forward to those.
Cool. Well, thank you again for a really cool talk. We do not have a seminar next week, but we will have one on May 13th. Sean Elvidge will be continuing our kind of discussion on the thermosphere, and we'll be discussing the thermosphere and extreme value statistics. So I hope to see everyone in 2 weeks' time. And thanks again, Dan. I hope everyone has a wonderful week.
Yeah, thanks. Bye, everyone.
Thanks. Very interesting.
Thank you. Bye-bye.